Okay, well, now let's look at what we can do with Schrodinger's equation. The first thing we'll investigate is how we can use Schrodinger's equation to propagate the wave function forward in time. Hang on. So, so using Schrodinger's equation, we can propagate the wave function forward in time. All right? What does that mean? What I mean is that given psi of x at some time t0, we can find psi of x at any other time. I say propagate the wave function forward in time, but actually the same technique lets you propagate backward in time too. Okay? And all that we're going to do is to numerically integrate Schrodinger's equation. The same trick works with any wave equation, by the way. But here, we'll use Schrodinger's equation. Suppose we know the wave function at one moment in time. I'll suppose that moment in time is t equals 0, just to make my notation simple, but it could be any moment. Okay? Then at any later time, then one moment later, psi of x and dt, the wave function will be given by this. The original wave function plus the rate of change of the wave function at time 0 times dt. Okay? This has to be true as long as the time increment dt is small enough. Then we can find the wave function a moment after that by repeating the process. Okay? And of course, we can repeat the process over and over again to find the wave function at any time we'd like. What we've sketched out here is a very simple way to do numerical integration of the wave function. Okay? And this scheme would work perfectly well. If you're a computer scientist, you know that there are actually more elegant ways to do this, but they amount to pretty much the same thing. Secondly, if you're wondering about the time derivative of the wave function, notice that that's exactly what Schrodinger's equation gives us. We can write the Schrodinger equation this way. The time derivative of the wave function is 1 over IH bar, or equivalently, minus I over H bar, times minus H bar squared, excuse me, over 2m times the second derivative with respect to position of the wave function, plus u of x times the wave function. Okay? So that's all we need to do, and we can propagate the wave function in time. If we know the wave function at one moment in time, then we can find it in the future. All right? Terrific. Here. Now, I'd like to illustrate this with an example, and the example we'll use is a free particle, but I'll just mention that this is not a task for a pencil and paper, all right? It's a task for a computer to do this repetitive numerical integration over and over again. So we'll do this on a computer. But older textbooks like ours don't talk about this very much because it requires a computer to do anything. But, you know, there are computers all over the place, right? It's not a big deal. In fact, what I'd like to show you is that we can use numerical integration to look at the time evolution of all kinds of waves. And so in a moment, we'll take a look at mechanical waves or simple waves, okay? Um, at heat diffusion, what are sometimes called heat waves, and finally matter waves. In each case, we'll just propagate a different wave equation forward in time using this technique. Here, hang on for a second and we'll take a look. All right, well, here we go. So the first equation that we'll numerically integrate is the first one here that describes a simple wave. A simple wave moves at a constant velocity, no matter what the frequency. The velocity is independent of frequency. There we go. We've looked at something like this before, but this is different because here I'm not starting with a solution. I'm just numerically integrating the wave equation, starting with an initial condition that looks like this wave packet. All right? But what we get is exactly what we saw before, a waveform that moves forward in space and doesn't change its shape as it moves. All right, well here, let's look at a different wave equation. This equation describes heat diffusion. The temperature as a function, the rate of change of temperature as a function of time is equal to a constant times the second spatial derivative of the temperature, okay? Sometimes called Fourier's law. Here, let's take a look at this. So we're numerically integrating the heat diffusion equation here, and we get something completely different. If the initial temperature distribution looked like that wave packet, then over time, everything kind of spreads out and flattens out as the heat diffuses outwards. Okay? It's kind of like a wave, but it doesn't really move. It just spreads out. All right? Anyway, that's the second equation. Now, finally, let's come to the one we're really interested in, Schrodinger's equation, which describes the propagation of, or the behavior of matter waves. And here we're going to be numerically integrating this. In this case, the potential energy is going to be zero. That is, we're talking about a free particle. All right? Let's go ahead. Now, we see the behavior actually that we saw when we talked about dispersive dispersion in waves. When we numerically integrate Schrodinger's equation, we get a wave packet that moves to the right, but also spreads out as it moves. Okay? And notice that in this case, the wave packet broadens as it moves to the right. Okay? That is, excuse me one sec. And in addition, you'll notice that there's this interesting behavior where the high frequency components of the waves, or short wavelength components, get ahead of the long wavelength components of the wave. Something we talked about a little while ago. Anyway, we can use Schrodinger's equation to propagate the wave function forward in time by numerical integration, as we can for all types of waves. This is sort of interesting, really, because it tells us that if we know the state of a system at one moment in time, we can actually predict deterministically how the wave function will evolve. The wave function evolves deterministically, but when we make a measurement, the results of the measurement are probabilistic. So it's only in that sense that quantum mechanics doesn't seem to respect causality, okay? Or determinism. All right, I think we'll stop this here. And then we'll go on to talk about bound particles.